Hi, this is Professor Dorr, and this is Lecture 12 of EE310. And this is a review lecture that's going to cover Chapter 8 through RMS values in Chapter 11. So Chapter 8 to partway through Chapter 11. And in this lecture, we're going to start off with the rules for inductors and capacitors. This is something that I present to students in a little chart here, and we found it very useful because I give you the verbal rules, which are for one side of your head, and then the equation for the other side of the head. So I'm going to review them here, but I really go through them in detail in Lecture 1 and Lecture 2 of this course. Then we're going to do initial conditions. We'll do some review problems on initial conditions, and then we're going to do an underdamped series RLC problem where we're actually going to get the voltage as a function of time. So we'll kind of go through the whole procedure. I'm going to go through the review of basic op-amps again for the ideal op-amp as a circuit element and do a couple of examples. And we'll go through AC circuits, and we're going to do a big Thevenin AC circuit problem with a dependent source in it. It was actually the little supplemental problem that I threw out a lecture or two ago. And then the final thing we're going to do in this lecture is calculate the RMS value of a sawtooth wave. So a lot of different stuff from Chapter 8 up through now, but stuff that I think is important as you go into this exam. So let's start off with the rules. And what the rules are these are things that are always true about inductors and capacitors, and they kind of relate to initial and final conditions, the kind of stuff that you do in Chapter 8. And what I tell my students is that for everything that you do with these circuits, for initial and final conditions, for RLC circuits, every rule has to be satisfied. So when you have it right, you can go down the rules and go check, 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 check. Everything looks good. Sometimes students will catch errors that they do because one rule was used correctly, but another rule seems like it's violated. And at that point, they know that they have to do something. So the deal on the rules is I've got the verbal side. This is the intuitive side. I don't know which half of the brain is which, but one side of the brain supposedly does the intuition side and the verbal side. And the other side is the equation side. And when I look at circuits like this, I tend to look at them intuitively and verbally quickly. And then I jump right into the equations. I've been doing it long enough that my verbal side and my equations are pretty matched up. What I tell my students is this verbal side, this is the way to put these rules from here down to here, where I hope that they'll end up after you take this class. So let's go through them. On the verbal side for the inductor, we can't change the current through an inductor instantaneously. And we can justify that many different ways, but what I'm going to do is I'm going to just put my equation here that says the inductor current at time equals 0 plus is always going to be equal to the inductor current at 0 minus. Right at that instant of time equals 0, from time equals 0 minus to time equals 0 plus, that inductor current won't change. And that inductor, you'll see later here that the voltage can change across the inductor, but the current through the inductor won't change at t equals 0. So similarly for the capacitor voltage cannot change instantaneously at t equals 0. So we say that Vc of 0 plus is equal to Vc at 0 minus. Now we've talked about two cannots. Let's talk about two cans now. The inductor voltage, it can change instantaneously. So we can't change the current through the inductor, but we can change the voltage across it instantaneously. And so what I have here is V sub L equals L di dt, which is our basic equation for an inductor that works anytime, any place, any problem. This will always work because it's basically the physics of the inductor. So if di dt changes, then the voltage changes. So we can change the voltage across an inductor quickly. Similarly, we can change the capacitor current quickly. And again, now I throw out the basic equation for a capacitor. It takes a while to get used to these because the inductor and the capacitor are duals of each other. And that actually has good mathematical or good circuit meaning. But an intuitive way we can think of that is they're real similar, but they're not quite the same. Real similar, they're energy storage elements. Except the capacitor stores energy in an electric field where the inductor stores energy in the magnetic field. So the capacitor, the energy is related to the voltage. The inductor, the energy is related to the current. But let's get back to our rules. The inductor current cannot change instantaneously, but the voltage can. For the capacitor, it's the other way around. The voltage can't change instantaneously, but the current can change instantaneously. That sometimes messes students up, so make sure you're cool with that. Make sure you got that. So we did our cannots and we did our cans. Now let's go to our steady state. And for the kind of circuits, for the circuits we work with, or the problems we work with in Chapter 8, there are two places where the circuit is in steady state, meaning nothing is changed. The way I like to think of steady state is nothing is changing, so all the derivatives are zero. So d anything dt in that circuit is equal to zero. So di dt, dv dt, all that is equal to zero at steady state. And the two places where the circuit is in steady state are at t equals 0 minus, because at 0 minus the circuit has been in that configuration for a, quote, long time and had lots of time to stabilize. And the other place where the circuit is in steady state is at t equals infinity. So the thud or the boing has happened and everything's settled out. And at t equals infinity, we're in steady state again. So these two rules are going to work for both of those cases. So in steady state, di dt, of course, is equal to 0. So the inductor voltage is 0. We can actually sneak up to our inductor equation and we say steady state means di dt is 0. So of course VL is going to be 0. And what I show here is VL of infinity equals 0. But it works at time equals infinity, but also for time equals 0 minus. Now at steady state for the capacitor, dv dt equals 0, because d anything dt equals 0. Let's just sneak up to our equation here. If dv dt equals 0, IC equals 0. So at steady state, the current through the capacitor is 0, and the voltage across the inductor is 0. Now, consequently, the current through the inductor can be whatever you want at steady state, but the voltage will be 0. And similarly, the capacitor voltage will be whatever you want at steady state, but its current will be 0. So as we've gone through all these thuds and boings, Chapter 8 kind of problems, when we've done all our initial and final condition, we've really appealed to these rules quite a bit, and that's why I include them in this lecture. Okay, let's do a problem. So we've got a circuit, and the switch has been closed for a long time, and it's going to open up at t equals 0, and we basically want to find a whole bunch of stuff. So I look at this circuit, and I'm just going to kind of triage it. Let's see, one thing I see is that when the switch is opened, or at t equals 0, I just have a series RLC circuit. That's nice, but that's not what I'm being asked for here. What else do I see here? At t equals 0 minus, the switch is closed. So what do I know? I know from my rule that I have no current in the inductor, and I have no current through the capacitor, and I have no voltage across the inductor. So therefore, there's no current down here, and there's no voltage here, so it looks like I just have a voltage divider at t equals 0 minus. So I can get that voltage pretty easily. What else do I know? I know that at t equals 0, I can't change the capacitor voltage. So whatever that voltage divider voltage was, I'm not going to change it. And I also know that I'm not going to change the current through the inductor. So this voltage is going to be the same at t equals 0 plus, but I'm not going to change the current in the inductor. So whatever current was coming from this end, from over here, when I open that switch, that current's going to be coming out of this capacitor because I can't change the inductor voltage quickly. Okay, so that's all good. What else do I know? I know that at t equals infinity, this switch is going to be open. And the intuitive, simple thing to say is circuit's going to be, quote, dead. There's going to be no current, no voltage. But there are cases where that's not actually the case. Ask an old person who worked on vacuum tube radios, and you'll unplug the radio and you might go in with your hands and get a 300-volt shock. Old people call that a doghouse circuit. So I'm careful about when I just say it's dead, but let's formalize that. So it's t equals infinity, and the switch is open. So obviously I got no current here. And I know I have no current through the capacitor. So that means I got no current here, and I've got no current here. So if this is 0 volts, and I got no current, I'm also going to be 0 volts here. And since I have no voltage across my inductor, I'm going to be 0 volts here. And I know I have no current through here. So yeah, all the currents are 0, all the voltages are 0. But you see that we formalized it. So now I've triaged this thing. So among other things, I'm not afraid of it anymore. I can get anything I want for this because I understand it now. So if you're taking an exam, this is a really good place to let that anxiety go down, because I've kind of followed this thing through. I've kind of figured out what happens, what goes where. I didn't use any numbers, but those just get in the way. But I'm cool with this circuit. So let's do the nitty-gritty here. Part A, VC of 0 plus. At t equals 0 plus, I know that I have no current through here, and I have no voltage across here. Now, some of you may want to draw little open stubbies here, and you might want to draw a little shorted stub here. And that's kind of nice when you're learning the material. I want you to understand the rules so well that you don't need to. That you just say, at t equals 0 minus, switch is closed, resistor, nothing, no voltage here, resistor here. I just got a voltage divider of 4 ohms and 2 ohms. So VC at 0 plus is just going to be 4 divided by 4 plus 2 times 12 is 8 volts. So now let's find IC of 0 plus. We're going to have to do a little work for this. So I got to know which tool to pull out of the toolbox here. I want IC, but I can't just go directly out after IC. I think the seagull has to peck around the trash can a little bit. So I'm going to look at the inductor current because I know it can't change. So I have a current through this inductor at t equals 0 minus, which is just 12 divided by 2 plus 4. 12 divided by 6 is 2 amps. So I had 2 amps at t equals 0 minus. That means I'm going to have 2 amps at t equals 0 plus. And the 2 amps, since I can't change that inductor current quickly, it's not going to come from here because the switch opened. So it's going to suck it out of the capacitor. And IC, a positive IC, is defined as going top to bottom. So that means the actual IC is going to be negative. And here it is. I sub L equals minus IC equals minus 2 amps. So IC is, so that was part B. Now let's get part C. dVC dt at 0 plus. Well, we know that IC equals C dV dt, so we can just solve that for dV dt, and we get I over C equals negative 2 volts per second. So that 8 volts we had here at time equals 0 plus, it's going down, and its slope right at 0 plus is going to be minus 2 volts per second. Now I want to find VL at 0 plus. Well, I know that I can change the voltage across that inductor quickly, and I know that this voltage isn't going to change at 0 plus. So remember, I want V sub L, VL at 0 plus. At 0 plus, this voltage isn't going to change. And this current is not going to change, which means that this voltage isn't going to change. So I started off with 0 volts. So at t equals 0 plus, I'm going to have 0 volts. So that was a little, may have been a little complicated. So let's use KVL. It's right down here. We'll go minus VC at 0 plus VL at 0 plus, which is the thing we're looking for, plus 4 times I sub L at 0 plus equals 0. So I wrote a formal KVL equation here, and now I'm going to just solve that for V sub L at 0 plus, and I know VC of 0 plus, and I know I sub L at 0 plus, and I get 0 volts. So formally, I got my 0 volts, but let's do it my informal way once again. At t equals 0 plus, I know that this voltage will not change because of the capacitor. And I know that this current will not change because of the inductor. If this current doesn't change, then this voltage won't change. So I've said this voltage won't change and this voltage won't change, so that means this voltage won't change. And I know that it was 0 at t equals 0 minus, so it's going to be 0 at t equals 0 plus. So back the video up a little bit if you don't understand that, because it's kind of a nice way to look at it. But the formal way, yeah, that's totally good too. All right. So I sub L at 0 plus, that's going to be the same as I sub L at 0 minus. And that was minus 2 amps, so we're going to come down here and we're going to put our 2 amps right here. Now I want dV L dt. So dV dt for the inductor. Well, that's kind of weird. Usually I get di dt for an inductor because V equals L di dt. But here I asked for dV L dt. So that's going to be kind of fun. So let's do it. VL at 0 plus is equal to 0. We know that. So that's equal to L di dt. So di dt for the inductor at t equals 0 plus is going to be 0. And that's also going to be dir dt, right? DIL dt is going to be dir dt because it's the same current. And so that means dVr dt is going to be 0. So I have a horizontal component. I know that dV dt on this side is going to be 0. What's dV dt going to be here? Well, remember we know that I equals C dV dt for the capacitor. And we know the current in the capacitor is minus 2 volts per second. So on this side, I'm going to have minus 2 volts per second, and on this side, I'm going to have 0. So dVL dt is just equal to dVC dt, is minus 2 volts per second. So this was the tricky part, or the hard part of this problem, and I want to show you a little trick that helps me, is when I have a horizontal component like this, what I'll do sometimes is I'll say, if I'm looking for the voltage across the component, I'll just say, what's the voltage on this side, and what's the voltage on this side, and then I'll subtract them. In this case, we wanted dV dt, or dVL dt, so I said, what's dVL dt on this side? And I find it's minus 2 volts per second. What's dV dt on this side? And it's 0. So I just subtracted them. And I find myself doing that for components that are written horizontally. I know that's kind of silly, but it's just kind of a survival tip for getting through this class. Let's do another problem. So in this problem, after being open for a long time, our switch is going to close at t equals 0. And we're going to find basically all the usual stuff. So let's triage the problem. So what do I see here? I see a 50 volt source. Switch is open at t equals 0 minus. That means no current here. So what do I know? I know that I have no current here, but you know, this side is not nailed down because it's open, so I think I'm going to start down here. The rules tell me that there's no voltage across the inductor, so I'm going to start at 0. I really should have a little ground symbol here. So I'll start at 0. I'm going to go up 0 because there's no voltage across the inductor. And I know that I have no current here because the switch is open. I have no current here because there's no current through a capacitor at steady state, because remember we're at t equals 0 minus. No current here, no current here. That means no current here. Now I could also say I got no current, I have no current here, so even though the rivers kind of diverged here, they came back together again. So if I've got no current here, I got no current here. So so at t equals 0, I basically have no current and no voltage in this part of the circuit. Now, at t equals 0, the switch is going to close. And I got a whole bunch of stuff here, right? And I know, but all this current is eventually going to go through here because the streams kind of separate, they come back together. So I'm going to say that I can't change this current quickly at t equals 0. Therefore, I can't change this current. Now, I also know I can't change this voltage quickly. So what do I know? I know that when I close this switch, I'm going to have 50 volts here. Since I have no current through here, I'm going to have 50 volts here. Now I could also say there was no voltage across the capacitor at t equals 0 minus, so that means there's going to be no voltage drop across the capacitor at t equals 0 plus, so my 50 volts here is going to end up here. So at t equals 0 plus, I have 50 volts here. Since I have no current here, I have 50 volts here. And since I could not change the capacitor voltage quickly, I have 50 volts here. So what let's do is let's look at this little part of the circuit. When the switch changed, all those three components went boink up to 50 volts. They all went together because there was no current through the inductor. So at t equals 0 plus, I got 50 volts right here and no current. And I go back to my rules checklist and I say, can't change the current through the inductor quickly? Yep. But I can change the voltage across the inductor quickly. I sure did. I went from 0 volts to 50 volts. So that's all cool. So now let's look at the circuit at time equals infinity. At t equals infinity, we're back at steady state again. So we're going to use our last two rules. I have no voltage across the inductor. I have no current through the capacitor. So some of you will put the little stubby things here and put a short here and a stubby things here that are open. You can do that. But what I'm going to do is I'm going to just say at t equals infinity, I got basically my path goes through the 20 ohms. Doesn't go through here because I can't have any current through the capacitor. So I go through here and then I go up here, down here. This voltage will be 0. So I can get the voltage across my capacitor pretty easily. It'll just be a voltage divider with these two resistors. So I've kind of triaged it, and I'm kind of comfortable with what I see here. So let's do the nitty-gritty. So I at 0 plus, where's I? Oh, here's I right here. And so what I'm going to say is that the inductor current can't change quickly. So I sub L of 0 plus is going to be 0. And there's going to be no current in the 20 ohms. Why is that? Because there's no current here. The stream split. I got no current here. I don't have any current in the capacitor because I can't, I'm sorry, I have no, I'm not changing the voltage across this capacitor, so I have no current through here. And if I have no current here and no current here, I have no current in the capacitor. So another way to look at this part of the problem, which is a little easier for me, is what were we asked for? We were asked for we were asked for I at 0 plus. Well, I know that the voltage across the capacitor at 0 minus was 0. I can't change it at 0 plus, so I got no voltage across here. That means I got no current. So the answer is 0 amps right here. All right, so, sorry, it's 0 amps here. So for part B, we want to find di dt, and that's di dt here. So let's see, that's kind of a weird thing to ask for. Usually when we ask for di dt, we're asking for di dt in an inductor, but that's not the case here. We're asking for di dt in this resistor. So that is going to be equal to 1 over R times dVc dt, or dV dt for the capacitor divided by the resistance is going to give us di R dt. Make sure you're good with that. So that's going to be 1 over R times IC over C, because remember I is equal to C dV dt. And we know that the capacitor current at time equals 0 is equal to 0. So we have 0 amps per second right here. All right. So now I of infinity. Well, at time equals infinity, the voltage right at the top of our inductor is 0 because we have no steady state voltage across an inductor. We have no current through the capacitor, so I've just got a voltage divider. And the current is going to be 50 divided by 20 plus 10 is 30. 50 divided by 20 plus 10, I have 1.67 amps. For part D, we want dVc dt. And we know that dV dt for the capacitor is going to be equal to I over C. And I is going to be 0 for the capacitor at time equals 0 plus. E, I sub L at 0 plus. So at 0 minus, we know we had no current for the through the capacitor. Why? Because we have, I'm sorry, I didn't say that right. We have no current through the inductor. Why? Because, yeah, we've got this little diversion of the current, but they come back together. So this current will always equal this current. And so we have no current in the inductor. That means we have no current in this resistor. So I sub L is equal to 0, and I sub L at 0 plus is also going to be 0. All right, so we want di dt for the inductor. And we know that V equals L di dt for the inductor. So to get di dt, we really want to get V over L. So di dt for the inductor is going to be the inductor voltage divided by the inductor value. And so remember, when we close this switch, we can't change this current quickly. Therefore, and it was 0 at t equals 0 minus. So that means at t equals 0 plus, this current is going to be 0 because this one's 0. So we have 50 volts here. We have no current, so we have no voltage drop here. So we have 50 volts here. And we know that we had 0 volts across our capacitor. And that's not going to change, so we're going to have no current here. So that means we have no current in our capacitor. So what happens? There's no current all the way through here at t equals 0 plus. Since there's no current, there's no voltage drop. So I have 50 volts here, and I'm going to have 50 volts here. Again, the way I like to think of this is since there's no current through this path, the voltage of all these components goes boink up to 50 volts. So the inductor voltage at t equals 0 plus is going to be 50 volts. So 50 divided by, 50 divided by the inductance gives me 166.7 amps per second. Now let's get Isabelle of infinity. At time equals infinity, the switch is closed and the capacitor has no current through it. The inductor has no voltage across it. So the voltage here is 0, the voltage here is 0. So my current path is going this way. So the current in that inductor is just going to be 50 divided by 20 plus 10, or 50 divided by 30. And that's going to give us 1.66 amps. So let's move on now to, I believe this is at the end of chapter 6. It's at the end of the lecture on generalized RC circuits, RLC circuits. And what I gave you is some nice little formulas that will work for the source-free case, they'll work for the step response, they will work for generalized circuits. If we go back to our second order system roadmap, what those equations do are they allow you to calculate A1 and A2. I don't know if you remember this roadmap, but we used it, I believe, in lectures 5 and 6 quite a bit, because we took all these chapter 8 problems and said, they all fit on this silly little roadmap. And you remember that what we start off with a circuit, we do all of our initial and final conditions, which is what we just did in the last 2 problems. But then we have to get the topology of the circuit and figure out what S1 and S2 are, and that tells us our equation structure. And then we compute A1 and A2. And these generalized RLC circuit, or this, what I'm going to come back to in our review lecture, is once we know what our equation structure is, how do we get A1 and A2? So let's look at that. If we have an overdamped system, then, and remember, it's overdamped. It could be a series, it could be a parallel, it could be a generalized circuit. This is going to cover all the cases. Just go back to the roadmap and you'll see that. So here's my equation for the response. And remember, I don't use V or I when I'm talking about just the response, because the response can be a voltage, it can be a current, it can be a pressure, it can be a temperature, it can be a displacement. All kinds of physical problems use these differential equations. But here it is. It's R sub S plus A1 e to the S1t plus A2 e to the S2t. And you calculated your S1 and S2 along the left side of the roadmap. And here is, these are the equations that describe what we're doing down here. But this is the thing you need for the exam. Here's how you calculate A1 and A2. Remember, you've got your S1 and S2 from the left side of the roadmap. You've got all this business from the right side of the roadmap. Put those together, you get A1 and A2. Now you know what to put in here. What's R sub S? It's the value of your response at infinity. And that makes good sense because these end up being negative, so at infinity both these terms are gone. So at infinity you're just left with this. So this is your V of infinity or I of infinity or whatever. But on the exam, I don't want you calculating all this. I don't want you taking this derivative. I want you to say, we use the equations developed in class and slap them into this matrix and use it. Now let's look at a critically damped system. And you remember you identified your critically damped system as S1 and S2 being the same when you were going down this path, and you flagged it as critical. And so for a critically damped circuit, you are going to want to use your alpha. Now remember, go back to lecture 2. When we get the roots of our characteristic equation, alpha is the real part of those roots. Somebody asked me that in the last lecture, and it was a really good question. Alpha is the real part of the roots. So here's our generalized equation for critically damped, and here's kind of how we get here, but these are the equations you want for your A1 and your A2. Now let's go to underdamped. So remember, here we had overdamped, we had a thud because we dropped our thing and it went thud. Critically damped, we had to come up with some kind of noise, so we called it a thump. But for underdamped, we got a boing. We drop our piece of copper pipe or our circuit or whatever, and we get boing, and there's a tonal component to it because we've got this damped sinusoid, and it goes ba. And here is our general equation, where we have our steady state value, of course, or our t equals infinity value. We get our omega d from our characteristic equation. And you'll see this in, it's actually lecture 3, I believe. But here's the math, but here is what you want to do on the exam. You know your dr dt, you know your alpha, you know your omega d. So you can solve this thing for A1, and you can solve for A2. So you can get A1 all by itself, and you can get A2 using what you got for A1. And let's make sure we make that a little clearer here. So we started off with this equation for R0 plus. And remember, you know this because you got that as part of your initial equation conditions, and you know your steady state values. So if I just solve that for A1, that's how I got A1 here. And then I get A2 by substituting my A1 plus the other things I know, and I shove them in right here, and I get my answer. And I got a boing. Okay, let's do another problem here. After being closed for a long time, that switch opens at t equals 0. So we want to get all the initial condition kind of stuff, but then it looks like we also want to find the capacitor voltage at t as a function of t. So let's look at what we're going to have to do here. First, we're going to have to get all this initial and final condition stuff. And once we get that, then we're going to go deal with the topology, but then we're going to put it together to get the response as a function of time. Now, the way I'm walking you through the problem, we're going to do this first. But we could do this first if we wanted. It doesn't really matter. Okay, and so let's say we were just asked to find VC of t. How would we deal with our initial conditions? Well, what I would do is I'd find VC at 0 plus, dVC dt at 0 plus, and VC of infinity, period. That's all I'd find. I'd find this, I'd find this, and I'd find this. In this problem, I just wanted to make it a little more miserable for you, so I asked you to find VR at infinity also. But to get VC of t, I want you to remember that if I'm asked for VC of t down here, then I want, or in other words, I'm asked for VC of t, I want the value at 0 plus, the derivative at 0 plus, and the value at infinity. That's all I want. Okay, so let's triage the problem first. So switch was closed for a long time, and so I had my 3 amps here, switch is closed. No voltage across an inductor at steady state, so the voltage here is 0. So that 3 amps is going up here, voltage is 0, so I got no current here. Voltage is, I have no current here because I have a capacitor. So that means my 3 amps, no current here, no current here. All that 3 amps is going right through that 2 Henry inductor. So I'm 0 volts here. Now I know that I have no current here. So I'm 0 volts and I have no voltage drop here. So that means I got no voltage here either. Good question. Do I have any energy in this series RLC circuit at 0 minus? Sure do, because I've got energy in the magnetic field of the inductor. So yeah, that thing, it's lit up and ready to go. Okay, so we wanted to find, actually, let's keep triaging. So, okay, now I'm going to open the switch. So I know I had 3 amps going this way, going top to bottom through the inductor. And I can't change that at time equals 0 plus. So that means that 3 amps has got to come this way, out of that capacitor and down here. So that means this capacitor is instantly going to start providing current. Can I change the current in a capacitor quickly? Absolutely. It's one of our rules. And what else do I know? I know that that's going to put a voltage. I can't change this capacitor voltage quickly, but I am going to get a voltage drop across here because of that current. So it looks like that inductor voltage is going to change quickly. So I'm going to have some di dt happening here. And since the capacitor current is going to change quickly, I'm going to have some dv dt going on here. So I'm going to have all kinds of fun. Now let's go to t equals infinity. At t equals infinity, the switch is going to be open. And that means no current here. I know I'm going to have no voltage here. I'm going to have no current through the whole thing because at steady state I have no current through the capacitor. So let's see. 0 volts, 0 volts because I'm at steady state. And so 0 volts here. So if there were, so no current here, so that means no current, no voltage drop here. So I'm going to be 0 volts here. So at t equals infinity, this thing's dead. I got nothing going on. No current, no voltage. Okay, so now I'm satisfied with my triage. So I am asked for VC of 0 plus. So the switch was closed for a long time, and at t equals 0 minus, I had 0 volts here. And I know I have no current here at t equals 0 minus. So that means I have no voltage drop here. So at 0 minus, I have 0 plus 0 times the resistance. So I got 0 here at t equals 0 minus. So that means my capacitor voltage at 0 minus is going to be 0. So VC at 0 plus is also going to be 0 because I can't change the voltage across that capacitor quickly. Okay, the next thing we're asked for is dVc dt. So I'm going to look at the inductor because my thought process says that in order to get dVc dt, I need to know the current through the inductor at time equals 0. And it's going to be driven by this inductor because I know I'm not going to have any current here. So at 0 minus, I had an inductor current of 3 amps. 3 amps going down like that. And at t equals 0, the capacitor has to supply the current. So that means in order to keep that 3 amps the same, it's not coming from here, so it's coming from here. So for the passive sign convention, my capacitor current is going to be negative 3 amps. So here it is, IC at 0 plus is minus 3 amps. So dVc dt at 0 plus is going to be IC over C, which is going to be minus 3 amps divided by 0.6 farad is minus 5 volts per second. Now let's get Vc of infinity. At time equals infinity, the switch is open, and so I got no current going this way. And because the capacitor were in steady state, I got no current this way. So if I got no current here, and I got no current here, that means I got no current here. And I know that this voltage is going to be 0 because I have no voltage across the inductor. So I have 0 volts, and then I have no current. So that means no voltage drop here, so I'm going to have 0 volts here. So Vc of infinity is equal to 0. All the energy is dissipated. Now it looks like I wanted Vr at infinity. And that is over here. Well, that's kind of a zinger, isn't it? But perfectly fair. The switch is open, so I got no current here. So all this current is going through that resistor. So let's say 3 amps times 2 ohms gives me 6 volts. Please say I got that right. I got it right. Yay. Okay, so where we are on the second order roadmap is we just did all this for Vc. Now, whether you're in my class or not, here's a trick for you. The British would call it a top tip. You're asked to get Vc. And what you're really doing is you're going to take everything you did and you're going to go down this path in the roadmap. So what I would recommend you do is I would take what you got here and restate it. Because you may have messed up here, but you want partial credit here. So what we're going to do is when I get to this stage here, and I didn't do it here, but do what I say, don't do what I do. I am going to write down my Vc at 0 plus, dVc dt at 0 plus, and Vc of infinity. I'm going to write it right here because I may have messed it up here, but I want the grader to see, hey, these are the values that I'm going to use as I go through the rest of the problem, and you'll get more partial credit for that. Okay, so what we're doing now is on our roadmap, we're going to go this path, where we're going to look at the circuit, get the topology, get S1 and S2, and get our basic equation structure. Then we're going to mix it in with what we got here and get our A1 and A2. So this is a series RLC. And so alpha is R over 2L is 0.6. Omega naught is 1 over root LC is 0.913. Now remember that alpha is different for a series or a parallel RLC, right? But omega naught will always be the same. Now, it's kind of silly, but I call alpha our thuddiness coefficient, and omega naught is our boinginess coefficient. Because if omega naught is greater than, here we go, if omega naught is greater than alpha, our boinginess is greater than our thuddiness, and we're underdamped. Similarly, if alpha were greater than omega naught, our thuddiness would be greater than our boinginess, and we would be overdamped. Of course, if omega naught and alpha are equal, then we're going to be critically damped. Now, I want to give you one more piece of insight here, is in this case, we have a series RLC circuit, so we quickly know what alpha and omega naught are. Let's say it's a generalized RLC circuit. In that case, you're going to get the roots of your characteristic equation, and they're going to be in the form alpha plus or minus omega naught, j omega naught. So if you have a generalized RLC circuit, you're still going to have an alpha and omega naught. Go back to lecture 3 because it shows how these are derived as a function of the roots of the characteristic equation. Again, thanks to the student who asked me to point that out, because I really appreciate that, because I hadn't made a big deal out of it, but it's worth making a big deal out of. Okay, so we said series RLC. We said thuddiness coefficient was 0.6. Boinginess coefficient was 0.913, so we got a boing going on. So what I'm going to do is I'm going to write my general formula. So I know my alpha, I know my omega d, I just need to calculate beta 1 and beta 2, or really A1 and A2 is kind of how I do it. So where I am is I just did all this, I've got all this, I'm going to put them in the mixer right here, and here are my equations. I called them B1 and B2, but really I call them A1 and A2 now. So this slide is a bit old. So I use the equations right off of our generalized RLC circuits. I get B1, I get B2, I substitute into our general formula, and you might notice you don't see V of infinity here. That's because it was 0. I really should have shown it, but I didn't. Do as I say, not what I do. I put in my B1, B2, here and here and here, and you can see B1 was 0, so I just ended up with a sign term. Okay, now I want to review the ideal op-amp again. And we use the ideal op-amp as just a circuit element. And I want you to see how simple it is to work with op-amps as part of this class and just have them in your arsenal. This derivation, of course, follows from the first several pages of the op-amp chapter in this excellent engineering book here, which is available for about 45 bucks on Amazon. So let's go through it. So we only need to know a few things about op-amps from an EE310 perspective. And first of all, no current flows into the two inputs, V plus and minus. Here's the V plus input, and here's the V minus input. So that's one thing we need to know. And V out is equal to this thing we call gain times the difference in the two terminals here, or V plus minus V minus. So It's actually what we call a differential amplifier because it amplifies the difference between those two inputs. The third thing that we have to remember is that the gain of the op-amp is essentially infinite. Or in other words, this value right here is pretty darn close to infinity. It'll be a few 100,000 or so, but we're going to call it infinity in our class. And so what we can say based on this comment is that if the output of the op-amp is somewhere in the range of, let's say, minus 15 volts to plus 15 volts, if that's the case, then the voltage at these two pins or inputs is going to be the same. Why is that? Let's say that the voltage gain is actually 1,000,000 and the output voltage here is 1 volt. So that means to get our 1 volt here, if this gain is 1,000,000, we had 1 microvolt between the two terminals. So the idea is that if the output is some reasonable value, then the difference between these two terminals is tiny because the op-amp is a differential amplifier. If we have 1,000,000 here and a microvolt difference, we have 1 volt. A microvolt might as well be no volts. So we're approximating the gain of the op-amp as infinite. And really, that's all you gotta know about the ideal op-amp. Of course, we can, if you continue reading in my book on the op-amp, it talks about how, of course, we have to have voltage supplies going into the op-amp because otherwise we wouldn't satisfy Kcl around the op-amp. Because we can put out a lot of current out this output, but we don't take any current in here. And there are other little non-idealities of the op-amp that you have to pay attention when you design with them. But these ideal approximations really describe most circuits very, very well. So this is all you got to know. So now let's work with it a little bit. The gain of the op-amp itself is infinite, but the gain of the circuits that use op-amps is not infinite. Sometimes that confuses students. The gain of the op-amp itself is infinite, but the gain of the circuit isn't. Why is that? Because we have feedback around the op-amp. So I want to know the gain of this circuit, or in other words, I want V out over V in. Because we're going to find that what this circuit does is it takes V in, it multiplies some number that's associated with this stuff, and we get V out. Let's figure out what that number that's associated with this stuff is. So I want to find the gain of the circuit. So let's do Kcl at the inverting, that's the negative, terminal. And we know that we have no current into V minus. And also we know that since V plus is equal to V minus is going to be 0. And so we can use that information to write ourselves a Kcl equation. So Vn minus 0 over R1, that's the current going this way, going from here to here, plus V out minus 0 divided by R2 equals 0. Because remember, we have no current going in here. So let's work with that equation a little bit. And we have Vn over R1, just move this over to the other side, and we get V out over Vn is equal to minus R2 divided by R1. And we call it the inverting configuration because we have a negative sign here. If Vn goes up, Vo goes down. I like to think of it like a teeter-totter. If this side goes up, this is always going to be 0. So this is kind of the fulcrum of our teeter-totter. This goes up, this goes down. And how far this goes down in relationship to how far this goes up depends on the ratio of the resistors. So this is a very, very common configuration for the op-amp. You'll see a lot of these in industry. A lot of op-amps use this way. And we derived this with resistors. But if we have capacitors and inductors and things like that, what we'll do is we'll say that V out over V in equals Z2 over Z1. Or in other words, I could have a bunch of capacitors and inductors that make some clump of circuitry between V out and the negative terminal. And that clump, the impedance of that clump is going to be Z2. Same thing here. I could put a big clump of stuff here. I could put a Thevenin equivalent. And Z1 is going to be this clump. So this is our inverting configuration. Let's do another. This one we'll see is what's called the non-inverting configuration. You'll see why in a minute. But I'm going to do the same strategy. I'm going to use what I know about the ideal op-amp. I know that the voltage across these two terminals will be 0. So if I have V in here, I'm going to have V in right here also. Second thing I know is I have no current going in this terminal. So what do I know? I know that I have V in right here, and I know that from the V in here, I know this current. It's going to have to be equal to this current because there's no current going this way, so I can get VO. But that was a lot of words. Let's write an equation. V in, go away. V in divided by R1, because remember, this is V in because there's no voltage here. V in divided by R1 is going to be equal to V out minus V in divided by R2, meaning this current is the same as this current. So I'm going to massage these a little bit until I get V out over V in. And I end up with the gain. V out over V in is my gain, and it's equal to R2 plus R1 divided by R1. Now again, for AC circuits, this could be a clump of circuitry. It could be a big parallel mess with series stuff attached, and it could have an inductor and capacitors and resistors, but that clump, that impedance between here and here is Z2. Similarly, the impedance from here down to here is Z1, and the gain would be Z2 plus Z1 divided by Z1. It's called the non-inverting configuration. It and the inverting configuration are probably going to be 80 to 90% of the op-amp circuits that you see in industry. And it's non-inverting because you don't see a negative sign here. If this voltage goes up, that voltage goes up. Now let's change this topology a little bit to get another very common topology. And we're not actually going to change the topology, we're just going to change the values. What I'm going to do is make R1 equal to infinity. That means it's like not there, right? It's an open circuit. So I ditched R1, but its value is infinity. And R2, I'm going to make that a 0 ohm resistor. It's going to be a short circuit. So it's going to look like there's nothing here, just a wire going from the output to the input. So that means R1 is infinity and R2 is 0. Let's look at the gain. R2 is 0 plus infinity over infinity. Don't tell the math department I did this, but that's equal to 1 in this case. And the gain would be equal to 1. So that's the third configuration that we went through in our lecture, but we're not really going through here, but it's the voltage follower configuration. Okay, so those are the basics of op-amps, and you can see that for an ideal op-amp, the analysis is really easy, and the circuits will typically fall into inverting, non-inverting, or voltage buffer. Of course, op-amps are used in all kinds of configurations, but this is mostly what you see in industry. If you see one that's not in this configuration, just write a couple of equations and you can figure it out. So let's do another problem. We want to find the output voltage for this circuit. So we'll triage it a little bit. I see an op-amp with its positive terminal grounded, and the input is going through this resistor to the negative terminal. Okay, so do I see one of my configurations? It's not that one. Look at this. Vn, go through something, and then have your other impedance going from your output back to your inverting input. Looks like this one. So I have an inverting op-amp topology. Now, just if I can digress for a second, a really good thing to remember is for the op-amp feedback loop to be closed, and the equations that we just derived fall apart if the feedback loop is not closed. The output of the op-amp should always be connected back to the negative terminal, because the op-amp works by negative feedback, and you're going to learn a lot more about that in control systems. But for now, make sure that whenever you look at an op-amp circuit, that output feeds back to the negative input. That'll save your butt in lab classes when you hook them up backwards and it doesn't work, and it might save your butt on a job interview too, because if you want to know if anybody knows anything about op-amps, just connect the feedback to the wrong terminal and see if they catch it. Okay, so we've got an inverting op-amp topology. Z2 is minus J16. Z1 is 20. So I'm going to use the formula for the for the inverting op-amp, and I'm going to get V out over V in is just negative Z2 over Z1. Do this on the exam. Recognize the topology, and then use the equation. Don't rederive it. Just use it. So here's our basic equation. So V out, which we're asked for, is going to be V in times minus Z2 over Z1, which is going to be 15 at an angle of 0, times a negative, that's this negative, negative J16 divided by 12, and V out is equal to J12. Pretty neat. It took V in and it shifted the phase by 90 degrees. Isn't that cool? So if I put a cosine in here, I'm going to get that cosine with a phase shift of 90 degrees. So another cool way we can look at this problem is, let's say I just put a step here. I just put 1 volt here. Well, for 1 volt, I'm going to have a constant current through here, aren't I? Because this is going to stay 0. I put my 1 volt here. My current is going to be 1 volt divided by 20 is some constant current. For the capacitor, remember, I equals C dV dt. And we know that current that we put in here is also going to be right here, because it has to come through here and it'll go out this way. So I equals C dV dt. So V dV dt for the capacitor is going to be a constant. This end of the capacitor is nailed down. I just made a ramp function. I put in a step, I get a ramp. By changing the capacitor or changing this resistor, I can change the slope of the ramp. I made an integrator. So it's an inverting op-amp circuit, but you'll see it called an integrator. But getting back to the problem, we looked at the problem, we recognized a inverting op-amp topology, we wrote down our equation for V out over V in, we substituted in Z1 and Z2, and out popped the answer. I want to go back to this supplement that I gave you a lecture or two back. And what I asked you to do was determine the load that could be placed between terminals A and B, that's here, that'll receive maximum power transfer from the circuit. Or in other words, I wanted to put my little dotted line right here, and you tell me what the impedance that I to put here so I get maximum power transfer out of this. As you figured out now, maximum power transfer, the concept is pretty easy. It's just ZL is equal to the conjugate of Z source, or the conjugate of Z Thevenin. So the work in these problems is really to represent your source as a Thevenin source so you know what Z Thevenin is. So in this case, we wanted to find the load that we could place between the terminals, and then we want the power delivered to the load. So our strategy is use KVL or KCL, do whatever you have to get V Thevenin. And for the Thevenin impedance, you can go in our textbook, Alexander and Sadiku, I believe this is for the 5th edition, to page 140, and it shows you a really cool way to handle these dependent sources where you just jam a little voltage or a little current in and you excite the source. And what's good about their technique is it'll always work. But in this case, we're going to find we don't need to do that. And we're going to stick with first principles. But you can do it that way too, and might be worth trying on your own. So the way I'm going to get Z Thevenin is I'm going to get the short circuit current here. So I'm going to short terminals A and B and figure out what the current is going through my short circuit. And then I'm going to take my Thevenin voltage that I already came up with and divide it by the short circuit current, and that's going to give me V Thevenin. So let's do that. First thing I need to do is determine V Thevenin for this thing. So let's do it with KCL. And so since I'm using KCL, I better label my nodes. Here's VA, here's VB, and here's VC. And so let's look at what I have. That dependent source could kind of get in the way of things, but we're not going to let us bother us. It's just 0.3 times this voltage. So it's just a current in my Kcl equation, and it's leaving the node. So I'm going to say it's positive, and it's just minus 0.3 times VC, which is cool because it looks like everything else in this formula. It just happened to be a dependent source. So 0.3 times VC plus VA minus VB divided by J3 plus VA minus VC divided by J2 equals 0. Beautiful equation for VA. So now let's do, let's separate that out into its It's VA, it's VB, and it's VC. Okay, now let's get node voltage VB. We look at it and go, well, that's easy. It's just 15 at an angle 0. Perfectly good equation. Now let's do VC. And I'm going to do the same kind of thing. It's going to be VC divided by 12 plus VC minus VB divided by J7 plus VC minus VA divided by J2 equals 0. I'm going to separate it all out into my VA, my VB, my VC. And looks like in this case, I substituted VB equals 15 at an angle of 0 into 1 and 2, and then I ended up with 2 equations and 2 unknowns. If I was being lazy, I would have left it in 3 equations and 3 unknowns, even though VB wasn't unknown. But either way, whatever works. So I ended up with VA and VC when I solved this complex matrix. And VC is just V Thevenin. So I got my V Thevenin. So some people like to use mesh analysis. So let's see if we can get VC using mesh analysis. So we draw out our 3 mesh currents, and we say I1 is just going to be equal to minus 0.3 times VC, because you can see I1 is the only thing we have here. And we have a negative sign because it's opposing the way this was drawn. And so that's going to be equal to minus 0.3 times 12 times I2. Because VC is just 12 times I2, right? So putting those together, I get I1 plus 0.3 times 12 I2 equals 0. So there's one equation. My next equation, minus 15 plus I2 minus I3 times minus J7 right here, plus I2 times 12 equals 0. And I'll massage that out to get my I2s and I3s separated out. And then I'll write my third equation, which is going to be around this loop. And it's pretty straightforward. Here's what we get. I take my 3 equations, I throw them into my matrix, and I get my I1, I2, and I3. How do I get VC? It's just I2 times 12 ohms, right? That's going to give me my VC. I2 times 12 ohms gives me V Thevenin, and thankfully it agrees with my mesh with my nodal analysis actually that I did before. So I got V Thevenin 2 different ways. They agreed. Did they agree the first time? Of course not, because I made mistakes, but then I fixed them. So now let's go back to our strategy. Our strategy is that I'm going to get Z Thevenin by taking my Thevenin voltage, or I'm going to compute my short circuit current for that Thevenin source. Or in other words, I'm going to short my output. And I'm going to get some current. And I know that that current is going to be V Thevenin minus 0 divided by Z Thevenin. So that means I can get Z Thevenin is just the Thevenin voltage divided by the short circuit current. So let's do that. So here is my circuit with the output shorted, right? This was my VC, or my output of the circuit, or my output of my Thevenin circuit, but I'm going to short it, and I'm going to get this current right here. And that's going to be my short circuit current. Okay? Now, what I can see here is that since VC was forced to be 0, this current is going to be 0, isn't it? Because remember, this is just 0.3 VC, and VC got shorted out. So I got no current here. So what we have to do is now we're going to take our topology and we're going to wiggle it around. So this is not here, okay? So what I'm going to do is I'm going to pick this, node up and move it over here, because really all this node is just J3 in series with J2, because remember this is gone because it's been zeroed. So this piece of the circuit from the 15 volts is actually shown by this right here, and it's in parallel with J7. So you just kind of have to do some two-dimensional visualization to see that. So what I really want is this current right here. So I'm going to, as you all know, I'm not in a hurry to use numbers. The short circuit current is going to be 15 volts divided by all this stuff, right? That's going to give me my short circuit current. And all this stuff is minus J7 in parallel with J5. So I really can't go any further now without putting in numbers, right? So 15 divided by J7 in parallel with J5. And in the numerator, I'm going to have my J7 times J5. The two J's give me a -1. The negative J here gives me another -1, which is why this is a positive 35 divided by the sum of the two components. So this is just the parallel combination. And I work all that out and I get my short circuit current. So now we'll go after that Thevenin impedance. So the Thevenin voltage divided by the short circuit current is going to be Z Thevenin. Don't think this model, don't think this model up here when you do that. Think of the Thevenin model where you just have the Thevenin source and you have a Thevenin impedance. If I short that Thevenin source out, then the short circuit current is going to be the Thevenin voltage divided by the Thevenin impedance. And so what we've done here is we've just found that short circuit current. We've just found that short circuit current. So we're going to take V Thevenin that we calculated before, divide it by that short circuit current, and that's going to give us Z Thevenin. Okay, let's move on, and we are going to work with a waveform here. It's a current waveform, and we want to find the RMS value of this waveform. And this waveform, we actually call it a sawtooth in industry. You can kind of guess why. But we see that it's a periodic waveform, and the period is 5 seconds, because every 5 seconds it repeats. So over one period, I of t is just a line. And a line has an equation m times t plus b. And of course, m equals 1, b equals 0. So here, the equation for the line is just I sub t is equal to t. So we're going to use our RMS formula here, and say that IRMS is the root of the mean square of the waveform. And so to get our mean square, we have 1 over t times this integral. This gives us the mean square. And we work out the integral and we get 2.887 amps. Now, is that a reasonable value? Well, we know it's not 0. We know the RMS is not going to be 5 amps, because if it was a DC value of 5 amps, it would have an RMS value of 5 amps. And we know it's going to be greater than half of this, or 2.5, because we're averaging the square. Okay, so that is our review lecture. As always, I look forward to having you in our next lecture, and I look forward to seeing everybody in office hour.